Okay, so in this set of notes, we're going to talk about what a buffer solution is. If you've read the text, which you may not have, you can try to define the term buffer. So take a moment and do that. Okay, a buffer solution is nothing more than a solution that resists change in pH when we add small amounts of acid or base. So the question is, how in the world can we do that? I mean, when we know when we add acid or base, the pH should change, right? It should become a lower pH if we add acid, and it should become a higher pH if we add base. Well, I'll explain. So a buffer is a solution, like I said, that resists change in pH when small amounts of acid or base are added. And buffers are typically an equal molar solution of a weak acid and a conjugate base. Now, the one I'm going to talk about is a mixture of acetic acid and sodium acetate. But really, any weak acid works. In Alka-Seltzer, it's got citric acid and sodium citrate. Sodium citrate is the conjugate base. Citric acid is the weak acid. It works to buffers. It just buffers at a different pH. Each combination will buffer at a different fixed pH. So like I said, an example would be a mixture of an example would be a mixture of acetic acid with this acetate ion coming from, say, sodium acetate. And here you can see I'm using 0.05 moles of each. Now, if we look at that system and we were to measure the pH of that mixture, it's about 4.76. Now, we're not going to go into an explanation of why. If you take AP Chem or college chemistry, you'll do the calculations and figure out why buffers have a certain pH at the beginning and the effect of adding small amounts of acid or base. You'll actually quantitatively calculate it. Now, the buffer we're using is acetic acid and acetate ion. When we add base, that's hydroxide ions, this is what happens. So the hydroxide ions react with the hydrogen ion of the acetic acid. So instead of hydroxide ions building up, they get converted to water, and we just make more of the acetate ion. Remember, pH is going to change if the number of hydrogen ions or hydroxide ions changes in solution. This prevents that from happening very much. So because OH doesn't build up, it gets converted to water, pH stays pretty much the same. Okay, same system, but now we're going to add some hydrogen ions. Okay, so in other words, we're adding some acid, a small amount of acid. That small amount of acid will react with the free acetate ions, forming more acetic acid. So the net result is when we add small amounts of hydrogen ions from an acid, they don't build up, they get converted into acetic acid, and the pH stays about the same. Now, this only works for small amounts of added acid or base. Now, I'm going to show data from a demo that I normally do in class, but since I can't do it this year, I'm just going to provide the data. Okay, so we got a buffer. This one was made of 0.35 molar acetic acid and 0.35 molar sodium acetate. So the molar concentration of the acetic acid and the acetate ions are the same. And we're going to compare that to water. Water does not have anything in it to buffer the pH. Now, pH of water was about 6.1. Slightly acidic. It makes some sense because a little bit of carbon dioxide dissolves in the water and makes a tiny amount of carbonic acid. So it's not surprising that it's a little bit on the acidic side of neutral. Now, we're going to add 0.02 milliliters of a 0.5 molar HCl solution, and we're measuring the pH. Now, we would be doing this with a pH meter and reading the digital output, but you can see it dropped a couple of pH units. So it didn't stay the same when we added a small amount of acid. Now, let's add twice the amount of base. So we're going to neutralize the acid plus have a little extra base and measure the pH, and you'll notice that it went all the way up to 9.48. So adding small amounts of acid or base to water changes the pH significantly. It clearly is not buffered. Remember, by definition, a buffer means that the pH won't change significantly. So we took a buffer made of this mixture of acetic acid and sodium acetate, and we added the same amounts of hydrochloric acid and sodium hydroxide, you can see the pH didn't change at all. Now, I wish I could demonstrate this for real, but it's the best I can do. Maybe I'll find a video of somebody demonstrating something like this. If I can, I'll post that as well. Now, remember, the key thing is small amounts of acid or base, the pH doesn't change. So I took this same solution after we played with it with a little bit of hydrochloric acid and a little bit of sodium hydroxide, and then I just overpowered it. I just added tons of hydrochloric acid. You notice that's 12 molar, 2 mils. Measured the pH dropped well below 2. Then I reversed that by adding tons of 6 molar sodium hydroxide, and the pH went way above 12. So you can see even a buffered solution isn't going to buffer large amounts of acid or base. If you get to AP Chem, you'll actually figure out what this term called buffering capacity, and you can actually figure out exactly how much acid or base you can add before you significantly change the pH. Remember, buffered solutions resist pH change when small amounts of acid and base are added. So all you really have to understand is the process. The process is when you add a small amount of acid, right? It's going to react with the conjugate base and not build up. The hydrogen ions won't build up. If you add a small amount of base, it's going to react with the hydrogen of the acid and it's going to make water, so the hydroxide ions don't build up. So with small amounts of either added, the pH doesn't change.